The goal of the lab was to explore the motion of diffusion and how it's affected by different variables. This was done by observing how different sized beads in various solutions moved under a microscope. After investigating, it was found that the beads moved faster when they were smaller and fastest in a soap solution rather than water or corn syrup. Before investigating, a computational model was created in order to simulate diffusion. The model showed two molecules, proteins and water, interacting. This relates to the lab investigation because theoretically the molecules in solution and the different types of beads will behave in a similar fashion. The main physics principle of the lab is conservation of momentum. Momentum is proportional to mass and velocity, as seen in equation 1. When two objects, or molecules, collide, the momentum before and after the collision must be the same, shown in equation 2. This can be applied to diffusion because as the beads move through the solution, they are constantly colliding with other molecules, even if we can't see them.
For this experiment, we decided that we were going to keep the size of the bead consistent while we changed the solution, and then kept the solution consistent while we changed the size of the bead. This would allow us to get results that reflected how each bead traveled differently through the different solutions. To prepare each trial, we had a group member take the tube, shake the tube 5 times. The same group member shook the tube the same number of times for each trial to maintain consistency. We then had an eyedropper take 1 drop, put it on the slide, put the slide under the already honed microscope. We then recorded and observed. Each video was then uploaded to Tracker, and we tracked the results to quantify how much each bead had moved under the given time interval. The realm of the model we were targeting was the mass of the beads. This influences the momentum of their collision. We also targeted how particles move through solution and how the properties of the solution influence the momentum of the particles. Based on our tracker results and what we observed when putting the slides into the microscope, it was clear that smaller particles move significantly faster through solution than the larger particles. It can also be said that the soapy solution allowed particles to move faster than the water solution, and the soapy solution allowed particles to move faster than the corn syrup solution.
The polystyrene beads were able to move through the solution due to principles regarding the conservation of momentum. We can assume the mass of the beads is much greater than that of the particles of solution because, at the level of magnification required to view the beads, the individual particles of solution remained invisible. Conservation of momentum states that the combined momentums before and after a collision must be equal. If the mass of object 1 is far greater than that of object 2, during an elastic collision, object 1's change in velocity will be small relative to its mass, meaning that because the beads were so much more massive, they were able to collide with the solution particles without losing much momentum. As for the difference in motion regarding the size of the beads, polystyrene beads with a diameter of 2 microns were massive enough to maintain relatively high velocity, while small enough to reduce the number of collisions with solution particles. 5-micron diameter beads, however, were voluminous to the point that the number of collisions with particles in solution prevented them from moving far relative to a fixed point. Relative motion of particles through various solutions can be best explained by examining the different intermolecular forces each solution exhibits. Molecules with stronger IMFs are better at attracting other particles, making it more difficult for them to pass through the solution. The viscosity of a solution is directly related to the intermolecular forces holding the particles of solution together, meaning that molecules with higher viscosity will likely have stronger IMFs. Corn syrup is an extremely viscous liquid, meaning that the attractive forces it exhibits are strong. Water, while not as viscous, is known to exhibit both polarity and hydrogen bonding, 2 extremely attractive forces. As for soap, its molecules only produce London dispersion forces, extremely weak IMFs. Because the attractive forces within soap are so much lower than those of water or corn syrup, the beads were more easily able to travel through the solution.
There were many sources of error in this lab, some of which include, while our group member was shaking the capsules, different amounts of kinetic energy was transferred to each capsule because it's very hard to keep your shakes consistent throughout the trials. Also, some of the trials took longer to load onto the microscope, which resulted in the beads being somewhat settled compared to the other trials. Despite minute things like this, I believe our lab was overall accurate and our results should reflect properly.